I'll take the.
This is my name. Oh, in there's chunk.
Excellent. Can I eat it afterwards? Can I eat it afterwards? Otherwise, I cannot talk.
Enjoy.
Thank you. Alright, okay. Let's just wait a minute or two. Have you had a chance to look at the homework?
For the ones due coming up?
Yeah.
I looked over it, yeah.
Makes. Oh, you haven't?
I haven't started it.
Yeah, but you've taken a look.
Yeah.
Does it make sense?
Yeah.
Honestly, everybody's in bed and no one's coming to anything. Two people. Let's see what is there. I don't know this action point. Which part is not here? Eric is not coming.
Who?
Eric is not coming.
All right, so I guess we can start. So again, when you watch the video, there's just a reminder that the second homework is up and it's due Tuesday. It's slightly more difficult than what you've done until now, but it builds up on it. Okay. So any general questions before we keep going with Navier-Stokes? No, all right. So last time we were talking about this pressure Poisson equation, right? And we started saying that, you know, P equal rho RT is how pressure and temperature are related. But in incompressible flow, the pressure actually depends on the velocity, right? So it's a function of the velocity vector. Okay, and so today we will see how exactly this pressure term is related to velocity by going through the conservation laws. Okay, so we were looking at the pressure Poisson equation. So the question is, how is pressure related to U? And the first thing we should do is write down our Navier-Stokes equation. So we have u by dt plus u dot lambda u okay, so this is the momentum equation. And then we have the conservation of mass. Lambda dot u equals 0. Okay. So let's take the divergence of the whole conservation of momentum equation. Let's take the divergence and the divergence operator just lambda dot u is the divergence operator. Okay. So what should we do? We will put let me see. Yeah, let me just do it here. So we do a lambda dot this whole thing. Okay. So what do we get? We get a lambda dot del u by del t plus lambda dot this big term, both lambda dot minus lambda b over rho plus lambda dot fine. So now we actually will go through each term and see if we can get rid of some of them or what they turn out to be. So can you immediately see one thing that we can get rid of? Let's start with the first term. Okay, nabla dot partial u by partial t. What can we do with that?
That would be 0.
Alright.
Del dot u would go inside the partial end.
Yeah, exactly. So we will
Continue.
take the nabla dot u inside the partial and then it would be 0, right? And we can do that because, okay, if we were talking about, if we were looking at 1b, we would have nabla dot del u by del t is just del by del x, and we have a del u by del t, right? And if we interchange the partial derivatives, we get del by del t of del u by del x, right? So we will do the same, and that's again assuming, you can do this if u is sufficiently small. So we'll do that here. So nabla dot del u by del t, as you said, we can write it as del. Okay. And you said that's 0 because somebody else, why did he say it's 0?
Here is no term which is dependent on time.
You're saying there is no term where?
No term, nothing dependent on time.
So in the momentum equation, that's the term dependent on time, right?
Yes.
If we take the divergence, we still have this partial in t.
Yes.
Okay? So there might be a time dependence. We cannot say with some logical or physical argument that there's no time dependence. If you think about flow, the flow keeps changing in time. So yeah, there might be a dependence. He said it's 0 because if you look at the term inside, what is it?
Conservation of mass.
Yeah, that's
will give you 0.
That's one of the conservation laws, right? So this is equal to 0 due to continuity. So the whole term is 0. Okay. So that's how we've managed to get rid of the first term. Yeah.
Just for local x, it's the term of local acceleration, so we cannot say never 0. Not never, but 90% we can't say 0. There will be always acceleration in the flow.
Mm-hmm.
So
acceleration is this du by dt.
So
okay.
For unsteady flow, we can't say it's not.
No. So this term is a conservation law. There's no assumptions in here.
Mm-hmm.
If we take the divergence, there's still no assumptions in here.
Yes.
Yeah, this whole thing is still perfectly valid.
Okay.
And when we interchange the derivatives, again, we did not make any steady assumption. The argument inside is equal to 0.
Mm-hmm.
So there's no point taking the time derivative. So this is not, there's no steady assumption. Oh, sorry. Yeah. Just in case that was hidden, yeah, so that's what we did. We interchanged the derivative in space and in time, and this term is 0 by definition, conservation of mass. So the first term goes away. Okay. So we can say this goes away. All right, let's look at the last term now. Okay, what about nabla dot nu nabla squared u? And let's assume that it's a nice normal fluid, so nu, the viscosity, is constant. So we can say this comes out nabla dot nabla squared u. All right, what should we do now? Should we say this is 0 as well? says yes, it is 0. Why?
Because you can change number square.
You're saying I can interchange nabla squared and nabla dot.
You can expand the y vector identity.
Okay.
So it will give you, again, 0.
All right. So you're saying let's expand and see what happens.
Mhm.
Fine. Let's do it. So I will need more paper. So let's expand the viscous term. Okay, so we want to know what this term is. And okay, do you remember what nabla squared u is actually? So if I just want to write this nabla squared u, it has, is it a scalar or a vector?
Scalar.
Scalar. Why is scalar? So if you remember, this term actually turns out to be nabla dot nabla u, right? And this thing was a matrix. Nabla u is a matrix, and when you take divergence of that, you get a vector. Just look at the notes from last time, and we actually expanded this term. So nabla squared u is actually d2u over dx squared plus d2u over dy squared. And then we have b. If I make a mistake, please point it out. C. Okay, what next? That matrix is just this term.
Yeah, so now you have 3 by 1 with each del over del x, del
Yeah.
over y.
Exactly. So we have the 3 components, and now we need to take the divergence. And we know nabla dot the matrix can be written as del over del x, del over del y, del z. Perfect. Okay. Fine. Let's keep doing multiplication. So we have I didn't write it out in a good way, so let me see if I can just do this. So this is vector A, this is vector B, so this is just A dot B, right, which expands out to del over del x of this whole thing inside, or U. Plus del over del y and then the last one, del over del z. Okay. All right. What next? So if you look very closely, you will notice that. What were you saying?
Nothing.
All right. No, go ahead. All right, you don't want to. All right, fine. So let's see. So if we take 1, 2, these 3 terms, what we can do is just looking at those 3. This is basically del 2 over del x squared of del u by del x. over del x squared of del v by del y x squared of del w by del z. Is it clear what I've done? I've just taken these three terms and exchanged the derivative. So this del by del x goes inside, del by del y goes inside, comes here, del by del z goes inside, comes here. All right, and now, and there's other terms, similar other terms. But what do we have now? Yeah, what can we write this as? The three terms. Let's group the second derivative in x and put it outside. Yeah. So we would say it's del 2 over del x squared. And we have del u by del x plus del v by del y plus del w by del z. Now does it look familiar? What is it?
This term is
It is?
0.
Yeah, this term is 0 because this is exactly equal to lambda dot u. Right? And we're talking about incompressible flow, so we know this is 0 by definition. So this whole thing is 0, which means, and so I've only done the expansion for the first terms, right? When you do the same thing for the second ones and the third ones, you'll get the same exact thing. Okay? There will be a partial in y and a partial in z outside. But inside you'll always get this, lambda dot u. Okay? So that way we can show that the whole viscous term, the divergence of the viscous term goes to 0. Okay? If and only if lambda dot u is equal to 0. Okay, so if I bring back the big equation we wrote, so we got rid of the first term and now we have gotten rid of the last term. Make sense? Okay. What next? This one is also 0. Right or wrong? This whole term will also be 0. Is that correct or not?
Because the second term is 0, is that the
second term.
del dot u dot
Yeah. That's the
and
question.
the parenthesis in 0?
You're saying the term inside the parentheses is 0?
Just no. I mean,
It's not necessarily 0, right?
Yeah.
So it turns out that, okay, it was convenient for us, we could get rid of the first term and the last term, but nothing else actually goes to 0. So this is what remains, okay? So let's see. What remains is lambda dot u dot lambda u is lambda dot minus lambda rho over p over rho. The other terms have gone to 0. Okay, now, when you take the divergence of this whole thing, what happens?
It gives you the power.
Once more? Say it, don't be shy.
It's the age of I'm not existing in class view.
All right, okay, so when you take, so this is just a derivative, right? If we talk about 1D, this would be d by dx. And there's two terms inside. So we logically should take the derivative of both of them, right? This is the chain rule. But again, let's say the fluid is homogeneous. There's no dependence of rho on space. So we can assume that's a constant and pull it out. So we have a minus 1 over rho nabla dot nabla p. What is nabla dot nabla p? There's a simpler form we can write it as. It's called the Laplacian. Nabla squared p. Right? And on the right hand, on the left hand side, we have the same u dot nabla. Okay. So it might be tempting for you to think that, okay, there's a nabla dot u. We can set this to 0. But no, actually it turns out it's not that straightforward. Again, we need to expand it using the matrices that we have seen before. And we will see that this term does not go to 0. But now we actually have our Poisson's equation, the pressure Poisson equation. This is minus rho nabla dot u. Okay, so this is the pressure Poisson equation. So what is this equation telling us? If I know the velocity at all grid points in my computational domain, if I give you that, you would compute the derivatives listed here, and then you would solve this Poisson equation to give me the pressure. Okay. It turns out that solving the Poisson's equation is the most expensive step in all of Aristotle's. So solving the pressure Poisson equation can take, let's say, more than 70% of the total computation time. It's closer to 90%, and it's the most troublesome thing to do in computations. So people have come up with many clever ways of doing this. You can use FFTs, fast Fourier transforms, to do this very, very efficiently. Or you can use another method called FMM, fast multipole method, which again solves Poisson equations in general, not just the pressure equation. If you're talking about gravitational forces, you get the same mathematical equation. So people have been working on this for a long time. And again, you don't have to reinvent the wheel, we can just use what they have come up with. Okay? All right, so let me just write out what this might, this still looks a bit mysterious, right? There's a lot of nablas and nabla u. Let's just expand this whole thing in 2D just to see what it looks like. So let's expand the pressure Poisson equation. In 2D, right? So, all right, I will need your help. What is the left hand side?
It's partial p squared or partial x squared plus partial p squared y partial y.
Anything else? No, that's it. Fine. All right. That's relatively straightforward. So let's go for the right hand side. And let's just do the nabla dot u dot nabla u. Okay. Okay. So this will take a bit more time. Where should I start? What should I start with?
In the parentheses.
Let's start with the parentheses, right? So let's see. So we get a nabla dot, and let's put a huge bracket. Okay, so help me expand the parentheses into the.
So is x partial u partial x
Okay,
plus u partial
right.
u
So,
partial y?
all right. So you're giving me the answer. What should we do? We should use, let's say, the matrix form we talked about the last time for expanding this. Yeah. So let's say
It can be
it's exactly what you're saying. We should first write out nabla u as the 2D matrix. So it's u partial x, right? And then you have a u with y, and then you have a u with z.
we don't have it.
We don't have a u with z. We're only talking about 2D for now. So let's see, just to make our life simpler. Fine, we have this matrix. So this is nabla u. All right. What next?
Times u and v.
Yeah, so we have a u dot here, so we can put a uv here. Fine. Okay, let's keep going. So what we get is this is equal to nab dot this times that u del u by del x plus b del u by del y, and this times that. Just u del v by del x plus b del v by del y. Okay, final step. What is the final step? Somebody else.
Again, another part. Very good.
All right. Yeah, fine. So yeah, we would take the dot product with this nabla, right? So it's just a basically. Let me just write it out, right? So you all, yeah. Okay, yeah. This.
So the final I think is partial u partial x over partial. So is partial u partial x squared plus u partial x times partial. What was it?
Okay. Yeah.
Sorry,
So let's go step by step. Right? Even I don't remember what the final answer should be. So let's see. So we have a del by del x of the first component, del by del y of the second component. So we have a u del u by del x plus b plus del by del y of a u del v by del x plus b by del y. Okay, and now it's just expanding and chugging through the numbers. So let's do that quickly. So this becomes if I take the derivative of x with respect to x of this term,
Partial u partial x all
Okay.
squared.
plus
Plus partial square u over partial x squared times u.
so that's just the first term. Okay. Second term,
Second term plus partial v partial x times partial u partial y plus partial u squared partial y squared times v.
okay, so that's the first bracket. Now the second bracket is
Second bracket.
Fine. So now let's see. If we start thinking about combining things now. Can you tell me immediately what that term will be? Somebody said 0.
Is 0.
It's 0. All right.
One continuity is inside.
Exactly. Again, we have a hidden continuity inside. Right? So let's see. If we write this out as, this is in u del to u over del x squared plus del to v over del x del y. Okay? And if we keep going, this becomes u del over del x. Okay, so I've just taken one of the derivatives in x outside, and what I have inside remaining is nabla dot q. This is equal to 0. The same way you can do the same thing to which one?
The last term on the first line, v, yes, and the last two terms. No.
Yeah, we can do the same thing here.
Yes.
Yeah, just as we realize these two combine to become 0, these two also combine to become 0. Okay, so in the end, what we have left is nabla dot u dot nabla u is not entirely 0. It's 3 terms that remain. Did I make a mistake here?
No. It's a square just.
Shouldn't that be a y?
This term is not the square u over number.
This should be a y. This is a y.
Yes.
Yeah, this should be a y. D by del y whole square. Okay, what was the other mistake you were saying? Okay, so this was one of the terms when I took the divergence, and it's not entirely 0. Some of the terms inside are 0, but we have something remaining. And if I know u, I can differentiate in x. If I know v, I can differentiate in y. And again, this gives me the right-hand side. Okay? So our pressure Poisson equation finally becomes del 2p over del x squared plus del 2p over del y squared equal minus rho times this whole thing, del u over del x whole squared.
So we can simplify it, I think. Partial u over partial x plus partial v partial y all squared, right?
No, see, this is a v and x, this is a v and y.
Oh, sorry.
So yeah, we can, I wish we could, but we cannot, so. Okay, so this is the pressure Poisson equation into D. Now it's much less, hopefully it's much less mysterious. So we started with this nice compact vector equation, and then we've just expanded it out explicitly in terms of u and v and partial derivatives. Okay, so why did we do this?
For the momentum equation.
We did this for the momentum equation. What do you mean?
The divergence of the momentum equation?
Yeah.
I don't know.
Yeah, that's how we started, right? That's how we got here. We took the divergence of the momentum equation to derive that pressure depends on velocity through this equation. But do you remember why we're after pressure in the first place? Why do we care about pressure? We wanted to solve our Navier-Stokes equation, which, just give me the velocity and how it changes in time. Okay. But in the momentum equation, there is a pressure term. Okay. So that's why we started looking at this. How can we compute this pressure if we know the velocity? Okay. So let's write out the Navier-Stokes equation. Let me see if I missed something. No, all good. Okay. Just a few notes before we do that. So, one. So this is the most expensive part. Of Navier-Stokes. Two, do you remember what classification this PDE is? F plus squared P equal F. This is
Poisson? No.
yeah, this is a Poisson's equation, but is it a hyperbolic PDE or something else? This is actually called an elliptic PDE. If you go back a few lectures, you can check the definition of elliptic. And we know that this is a very, the solution of P here changes very violently if you disturb any point, even very slightly. Okay? So the solution for P changes abruptly if if we introduce a disturbance in F at any point. Also, this change, every point affects, if you disturb F at any point, all points in the domain are affected. Okay. Does this make sense? No. So, imagine the surface of a lake, okay? And, it's calm and smooth, and you drop a tennis ball at one end. If it's incompressible flow, the assumption of incompressible flow says that the pressure change will be instantaneous throughout the lake. Okay? Every point, if somebody's measuring on the other side of the lake, they will see an instantaneous change in pressure because I've dropped the ball. The surface waves do not need to go there. Okay? That's what it means physically. And it might seem a little unrealistic, but it's a very good approximation. The information travels so fast that it's almost instantaneous. So change in F at any point x, y impacts P at all x, y instantaneously. Does this make sense now? You don't believe it?
No, my question is, what is the relationship with that elliptic, with that equation mathematically?
What is the relation of this behavior with
This behavior with the...
So, the Poisson's equation is an elliptic PDE. Any physical phenomena that follows this Poisson's equation has this behavior. For instance, if you talk about gravity, right? You're talking about, let's say, what is the gravitational pull on the Earth of this galaxy that's far, far away? Okay, so we would compute the force and the gravity potential and other things, and that actually follows a very similar equation: Laplace squared force equals something. Laplace squared potential equals something. And imagine that one of the stars in this other galaxy disappears instantaneously. It just disappears. Okay? So you have a change in the net mass of the galaxy. The change that we will feel on Earth, the gravitational pull, will be instantaneous. That's according to these simplified equations. Conceptually, that's what it means.
Yes, I understand this, but what about, how do you conclude this from the equation, this elliptic equation? I didn't get that.
Ah, okay. So, do you remember characteristics? We were talking about characteristics. No? Okay. So, a few lectures back, we were talking about characteristics of PDEs. And for elliptic PDEs, we realized that the characteristics were imaginary. There was no real characteristic solution. So that the slope of the characteristic represents the speed of information. For now, it's undefined. So yeah, that's how it's related. More questions? This is a big problem. You will see if you start solving the Navier-Stokes equation, and you have a bug that messes up one point, the entire solution gets corrupted because of that one point. Okay. If compressible flow is slightly more forgiving, because the mess up there will take some time to propagate. But that adjustment is instantaneous in the incompressible solution. More questions? Okay. Fine. So we know the relation between P and its dependence on U. Let's go back to what we were trying to do, which is solve the momentum equation. And let's stick to 2D. So going back to the momentum equation. In 2D. Okay. So again, I don't remember the individual parts, but I do always remember the vector form. So let me write it out. Okay, so in 2D, this has two components. The first component is
U dy.
u dy.
No. T, I think. U u partial x plus v partial.
Yeah, see, it's always confusing, so you can always just go back and write out the yeah, I mean, I get confused even to this day sometimes. So what I do is I can just write the u dot thing as the thing that I'm trying to explain. So now, can you tell me now?
U partial x plus v partial y.
Perfect. Then?
So we don't need the other term?
We do need the, so we need to expand the right hand side.
No, u partial v partial x plus.
Oh, this is the first component, right? Oh, we're only talking about this is the first component. We will write out the second component after this. Okay. Does this make sense? Alright, find the C.
Minus partial p partial x over rho.
Yeah.
Plus new partial u square plus x plus over v square.
V? Y, yeah.
Yeah, y.
Okay, so that's the first component. How does U change in time? We need the second one. So how does V change in time? Okay, what goes here?
U partial V partial X plus V partial Y.
Yeah, see, it's always helpful to just write this simple thing, and now you can just go boom, boom. That gives me this. And on the right hand side, we have the y derivative and okay, so into these, we have these two equations, second component. And from what we have learned up until now, we know that we can start discretizing this. We know how to discretize the time derivative, the convection terms, the diffusion term, and this is a simple first derivative. Okay, so let's see. Let's discretize. Let me take the second component and discretize it. So what do we have? Yeah, V what?
Vi at n, Vi plus 1 at n ij.
We're taking the time derivative. So we have a Vn ij. Make sense? Yeah, all right, perfect. And then the convective term, let's say we will upwind, and so we have a Uij, and derivative in x is
Upwind is Vij I plus minus Vi I minus 1 and j.
all right, perfect, yeah. So we have assumed that this is greater than 0.
This is greater than 0.
Same on the other side. Ij and j minus 1 over delta y. Okay. And now we have this is partially in y, so what should I write? Let's see, I should write j plus 1, j minus 1, 2 delta y, and the last one is v I j minus 2 I j.
I think just the typo. I think that's
Oh, where?
Vij times that parenthesis.
The first line, last term.
Oh yeah, sorry. There's not a plus times. Thank you. Let's see. All right, perfect. No, P. There was another typo here. It's a D. Okay, so we have this huge thing. In 3D, there's like 70 more terms. But is this all we need? Can we start solving this now?
No.
We cannot start solving this. This was the problem. We don't know P, and you can put an N on all of them. Okay, there's an N. The problem is still we did not know P. But now we said, okay, if we can actually figure out what P is by solving this pressure Poisson equation. Right? Yeah, so you could technically solve for P at N if you already know U at N and V at N. So we could solve for Pn since we know un and pn. Now, assuming that's true, do we have everything we need? Somebody was saying no, why no? So let's go through the terms, right? So at the current step, we know what V is, we know what U is. We can figure out what pressure is by solving the Poisson equation. Everything is known here. So technically, I can move forward in time. The only unknown is this Vn plus 1. Am I right or wrong?
What about Vi minus 1? J, we have that.
So all the space indices, think of the 1D example we did, right? What happened was, in the rod, you would cut it up into different points, right? So everything was known at a given n. So all the i's and I minus 1s and j minus 1s are known as long as it's at n. What we're trying to do is go to the next step, n plus 1. So everything here is known. So there's nothing that stops me from taking everything to the right-hand side and multiplying and dividing. That will give me the Vn plus 1. Turns out that, yeah, you can do this, but there's a problem. Does anybody know what the problem is? What?
Stability.
Stability is a problem? Why do you say that?
Depending on your grid.
So you're talking about the CFL condition and the stability of the diffusion equation that we had derived.
Diffusion term.
But that's fine. I mean, we have done an upwinding here, and we will make sure that the time step we take is small enough that we don't get this instability. Okay? So I will tell you, we can take very tiny time steps and solve this. Your solution will be stable. But there will be still a slight problem. Anybody have any idea? I mean, if you don't know, it's difficult to see. Because that's what, logically, this is what the first thing people tried. And when they tried it, they realized that this approach does not conserve mass. Oh, go on, sorry. No, all right. So,
This is why we are using working on node points for velocity and cell centers on pressure in 2D.
no, that's not the reason. That's for another whole reason. That's for odd even decoupling.
Okay.
So we will come to that later. So, all right. Logically, we could solve for Vn plus 1, but it turns out that the resulting Un plus 1 and En plus 1 do not satisfy continuity. Which is lambda dot u vector n plus 1 is not equal to 0. That is a big problem because we said to conserve mass, we need this to be equal to 0. Is it clear what the problem is? All right, so how should we solve this? People tried many different things for several years, and they were actually able to identify the best way to solve this Navier-Stokes equation so that you are able to enforce continuity.
Sorry, why not satisfying continuity?
There's many things happening here, right? There's errors in terms of discretization errors, there's precision errors, and all of this keeps piling up. And when you solve for B and U, you are not imposing this condition that at the next step it should be equal to 0. All we did up to this point was we said we can solve for P from the current U and V. Okay? If the current U and V satisfy continuity, that's okay. That just gives me the pressure. But when you take the next step, you have not enforced any constraint that the new velocity vector should satisfy continuity. Make sense?
I mean, it should satisfy, but it doesn't. I can conclude from the equation that it doesn't.
Tell me why.
Is that like other calculations to prove that it doesn't, or
If you think about what we are solving here, right?
the momentum equation?
Discretize the continuous derivatives with these finite difference approximations. Okay. And you're introducing discretization errors. Again, if you remember a few lectures back, we looked at this numerical dissipation, right? So what you're solving might not be the same thing as the continuous equation. Also, when you advance the momentum equation, you're not advancing the mass equation, which is continuity. Okay, so we should go a little slower here, because this is an important point. When I have written out this expansion, I've only used the momentum equation. The momentum equation is not directly related to the mass equation. Make sense? So if I move forward in time with the momentum equation, the mass equation is still waiting. We haven't used it in any way. So why should it satisfy continuity? Why should the new solution satisfy continuity? It's a very special condition, lambda dot u equals 0. There is no reason for the new solution to satisfy continuity. Does that make sense? So the fix is we enforce continuity in some manner. Okay. So that's what people were struggling with in the 60s and the 70s. How do we make sure that this continuity is satisfied? Okay. And yeah, logically this makes sense. This is how they started out looking at these things. Okay.
Basically, we are checking if this satisfies continuity or not. I mean, it has to satisfy, but we are not sure that it satisfies or not.
No, if you code this up and you solve in time, you can show that continuity is not satisfied. You can show that the new solution you will give me, this is not valid. Okay. All right. So to fix this issue, we can turn to something called pressure projection methods. Okay. And this is a very standard method that's used in the majority of the software today. Most commercial softwares, the simulations I showed you, they all use this pressure projection method. Okay. All right. So, do you have more questions before we move on? Okay. So, what does the pressure projection method do? It actually takes the Navier-Stokes equation, this whole big thing, and solves it step by step. Okay. So again, I'll write the Navier-Stokes equation. Maybe it's So we have three important components in here. We have this, we have this, and we have this. So this is the pressure term. This is the what? Viscous term or diffusion term. And the other one is
Advection.
this is the advection term. If you remember, when you combine the partial entity and this, it's the material derivative. Right? It's the advection. Okay. All right. So the pressure projection actually uses the concept of the fractional step method. So let's see. Fractional step method. It just means we solve each component of the Navier-Stokes equation, or the momentum equation. Sequentially. Assuming that the other terms are zero. Okay, so the steps we might follow would be do the advection first, then do the diffusion, and then do the pressure projection. See, that's exactly the three terms that we have identified: advection, pressure, and diffusion. Or it's perfectly logical to say, fine, I like doing diffusion first. So you do diffusion, and then do advection, and then do the pressure projection. What is another way we can do this? There's three steps, right? So we can have more combinations. We can move the pressure projection up. Right or wrong? Okay, before you answer that question, is it clear what's happening? Is conceptually, does it make sense? This is a very, well, this is how you solve the Navier-Stokes equation. So it's important that if you have any doubts, ask me now. Right? Really, is it clear? Or it took me a long time to get this in my head. It's called fractional step, not fraction step. Fractional step. Okay, but we can do the advection first, diffusion then, and then the pressure, or we can do diffusion, advection, and pressure, but we cannot move the projection step in between, or any of them, or to the, well, we have to do the projection step at the last, because that is the one that ensures continuity. That is how we enforce nabla dot u is 0 at the next time step. Okay? Right? So, if we write, let's follow the first one, advection, diffusion, and pressure. If we write this out in terms of the mathematics, what we get is, let's see, so step 1, advection. Okay, I will just copy the advection part. You will say del u by del t plus u dot nabla u equals 0. See, all the other terms I have set to 0, I've only kept the advection term. That's the idea behind this fractional step. And this introduces an error in time. Okay. But it turns out that if you keep the delta t small enough, these errors are not too problematic. And remember, I mean, we have errors all over the place. When we discretize the derivatives, we are using finite difference, which introduces an error. And when we split it this way, it introduces an error. This is also called time splitting. It's also called time splitting. Okay, I feel like I have lost some of you. If you have questions, please ask me right now.
My question: why not? I didn't understand why not. We can solve pressure first, the pressure projection.
Okay, so the question is, why can we not solve the pressure projection first, then do advection and
Mathematically, we are putting everything to zero, right? That's how we solve the Navier-Stokes equation. The three terms, we equal them to zero.
So see, we have, this is no assumptions, full Navier-Stokes. Okay. The first thing we do is we only take the advection terms, others can go to zero. That is exactly what we have done here. We will solve this equation. You will get an intermediate solution. And then we will do diffusion with that new intermediate solution. You will get a second intermediate solution. And then we will do pressure projection with that second intermediate solution. And the way we will do this will ensure that the very final solution is divergence free. Let me write it out and then it will make sense. Okay? So, okay. Yeah, let me write it out and it will make a lot more sense. So let's see. So if we do this, so we know how to solve this, right? This is the advection equation. And we know how to solve, let's see, the 1D advection. We talked about this a while ago. So when we do this, let's see, you might do un, no, not n plus 1. Now this is a u star. Let's see, this is let's take 1D, okay, 1D. So you would have an I, J, K, but let's keep things simple for now. You have an I here, and delta x 0, you have an ui minus 1, and n. Is that okay? I have just discretized the advection equation here. I know all of this at n. I can get my u star. Gives me u star. Gives me u star, which is an intermediate solution. Fine. I take this intermediate solution and I go to my step 2. Step 2 is diffusion. Okay, so we have nu del 2u over del x squared in 1D equals 0. This also we know how to solve. Okay. Before I give you the answer, what do you think I should write for the d2u over dx squared? We know how to discretize the second derivative. So what should I write? I'm sorry. This is not right. This is not right. It said du star over dt is equal to nu d2u star over dx squared. Yeah, this is correct. Okay, so what this is saying is the first change in u happens because of advection. And this new solution, u star, is responsible for the next change in u in time. Time splitting. You split your full Navier-Stokes equation into individual time derivatives. Okay?
Question.
Yeah.
We have to put every other terms to 0, right? Diffusion, so we have just diffusion, but partial u over partial t is a part of advection. Right?
It is, yes. How should I explain this? So the question is, this du by dt is part of the full advection term. Why do I have this in my equation again? Right? Okay. I have to show you the whole time error in time that we make when we split it like this with the full Taylor series analysis. I can do that next time, okay? For now, let's just follow the steps, okay? For now, okay? I will show it to you next time. So what we did was, first we did advection, others can go to 0, that's what happened. I get an intermediate solution, u star. Now, the concept of time splitting is, okay, my u star has to be diffused in time. And this is the diffusion equation. This is the heat equation, basically. dt or dt equal kappa, blah, blah, blah. This is exactly the heat equation. So my next advancement comes because of this diffusion term. Okay. And then we can write this as, what should I write the left-hand side as? Should I write an un plus 1 minus u star?
No, US star minus u I.
Okay, so what's happening now is I am at my intermediate solution. I have to compute another intermediate solution. Okay? And on the right hand side we have u and u star I plus 1 minus u star I 2 u star I. Is this okay?
Intermediate of intermediate, what does that mean?
Yeah, this is intermediate of intermediate. Okay, so u star star, and you will see exactly why, is another intermediate solution. Okay, and the last step is del u by del t, step 3. Is pressure projection. Del u by del t is equal to minus nabla p over rho. Okay, what should I write now? U by dt becomes so du by dt, now we've actually arrived at the last step. So the solution we will get from this will be our final solution, u at n plus 1. That's what we were after all along. Okay? Fine. But there's still the problem of this pressure. I don't know what this pressure is yet. Alright. We have 5 minutes. Let me just show you one more step. So,
Some question in Boca.
oh yeah, go ahead.
So in this method, we have assumed that advection is the fastest and pressure projection would be the slowest. That's why we have followed this.
You mean
And
the speed of solution, do you mean? No. What do you mean fastest?
So when we say that the change in velocity is first of all it's affected by the advection, then by diffusion, and then by pressure projection. But wouldn't it be this with pressure projection, because the pressure field, we solved the Poisson equation and we showed that the transmission of information will be instantaneous because of the pressure term.
Okay, I see what you're saying. So, before that, are you okay that you can do either advection first or diffusion first? Logically, there's nothing stopping you from doing that. Okay? And now you're asking me the pressure change on the solution, the influence on pressure is the most extreme. So I should solve that first. That's what you're saying?
Yeah.
Okay.
Yeah.
So the pressure projection, the pressure Poisson equation that we derived before this is exact. It's completely valid. But in this fractional step method, we are not using that at any point. Okay. We have not solved any Poisson equation yet. All we have done is solve the advection, diffusion, and now we will see what is the Poisson equation that we need to solve. Okay, so, but what you're thinking, I don't know how well it applies. Pressure projection is the fastest. Okay, I have to think about it, but the reason you have to keep the pressure projection the last is this is the step that enforces continuity on the new solution. And this is how it happens, okay? So, at this step, we need to ensure that, what do we need to ensure?
Continuity.
Continuity, nabla dot, what?
U.
U at star 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 something else.
N+1.
Exactly, U at n+1 should be equal to 0. Okay, we need to ensure that at this step. So, if we take the divergence of the full thing, U I n+1 minus U star star over delta t. Let me just replace the I with a vector equal nabla dot minus nabla p over rho. Okay, now we have something we can use. We have minus nabla dot p star star over delta t equal minus 1 over rho nabla squared p. Make sense? I haven't done anything, I'm just taking the divergence of this paper. Alright, so tell me, what happens to the first term? Yeah, we want this to be 0. So we get our pressure Poisson equation. Okay, now we have the pressure Poisson equation that we need to solve. If we follow these steps, make sense? Okay, I'm going to run out of time, so I will leave this for you to copy down, and then we can go further next class. And please remind me of your question again next class. Homework is due Tuesday. If you have questions, please email me, come to office hours, and yeah.
If I remember correctly, this is Chorin's project.
Yeah, this is Chorin's projection method, 1965 or something. Yeah, it's a very nice compact.
40 years. More
What?
than 40. It's been more than 40 years.
Okay. Yeah, this is called Chorin's projection method. This is the guy who came up with this. All right, the recording is